Okay. Hi, this is Luna from Amazon. It's my great honor to speak here about our project Ceres, where the goal is to harvest knowledge from semi-structured web. So here I'm putting a picture of the goddess Ceres, and this is a Roman goddess, and she is taking in charge of harvesting. And interestingly, the internal name for this project at Amazon is the name of another goddess of exactly the same responsibility, but different nationality. Okay. So before I talk about Ceres, let me give you some context about who we are, what we are doing, and why we do this project. So at Amazon, we are building a product knowledge graph. And the goal here is to build an authoritative knowledge graph for all of the products in the world, such that we can use it to answer any question about products and related knowledge in the world. And with this comprehensive and authoritative knowledge, we will be able to improve Amazon search, recommendation, and also voice shopping. Let me see. Okay, so let me first start with giving you a small example of knowledge graph for 2 songs. So it is a knowledge graph. So it is graph and has nodes and edges. Each node here represents an entity, and an entity could belong to one or multiple different types. And each edge represents the relationship between 2 entities. For example, here is a recording entity, and it is related to this entity, which is a genre, and also related to this entity, which is a person. And the relationship here is artist, and the person has name Taylor Swift, Taylor Allison Swift, and we see the date of birth. Now, let's squeeze this knowledge graph to one side and try to see what is the product side. So each sound recording is related to multiple songs, song tracks at Amazon. So those song tracks, they could have different formats and they belong to different albums. So that's the product part. Normally, when we talk about media products, we actually have a lot of data on the web from publishers, the media publishers, book publishers, movie publishers. They are very well trained to provide a lot of metadata, such as the director, actor, artist, release date, release country, length, and so on. And these are a lot of data with decent quality. Then the challenge here is different publishers, they will use different format. They will follow different schema. One source might call it director and the other one might call it directed by. And so the heterogeneity of the data is what we need to resolve, such that in the knowledge graph, we could have one ID for one entity, one person, and we could have one relationship to represent the particular relationship between 2 types of entities. And to resolve the heterogeneity, one of the most important techniques is entity linkage. In other words, we need to figure out that Allison Swift and Taylor Allison Swift and Taylor Swift, these are actually the same person. And in addition, if you want to be cool, you want to also figure out that if we see conflicting information from different sources, what could be the correct value? For example, if we see different date of birth for Taylor Swift from different sources, we need to figure out which one is correct, or is this unique and talented lady born twice? And after that, if you want to be sexy, you want to extract knowledge from the web. This is because there could be a lot of songs, a lot of books, and on the web, we can find comprehensive information about all of the different choices. And that's where we collect information about torso and even long tail books, songs, movies, and so on. So in our team, we have developed the entity linkage technique that could reach precision of 99% with over 90% of recall. And in addition, we developed web extraction techniques that gives us over 90% of precision. And we are applying these techniques to collect knowledge from the web. We use it to support 20 Amazon Music applications. We use it to answer questions from for Alexa. So far we have been looking at media products. The next example is about retail products. And here I'm showing you two examples for Tide detergents. So those are the two brown bubbles. And then we have the green bubbles represent the variations of the same product. So they are the same product, but have different size or maybe different scent. And in addition, we have those blue bubbles representing the properties of those products. For example, they have same brand, Tide, and they have the same function, detergent. They are of the same form, liquid. Neither of them is high efficiency. And we can see that the Tide detergent on the left-hand side, it has one extra function, odor remover. So for retail products, again, we still have a lot of data from manufacturers, from retail websites, but this time the data is of different quality. And to show you one example, here is a product chocolate gift box. This is from Amazon page. And we see that we have very limited structured information about it. Mostly we have is just in the title. Some of them we have bullets and the descriptions, but those are just the text information. We don't have that much of structured information. And on the right-hand side, we do see different flavors, different sizes. However, how many people would consider 1 pound red rose box as the flavor of your chocolate? And how many people will consider dark blue foils as the size of this chocolate box? And this is mainly because the information could be provided by the retailers for some particular purposes. And here it is to show the different variety. And so it is kind of an abuse of the attribute flavor and size. So the data here could be very sparse and noisy. And we can do the same thing by getting the data from everywhere and putting it together, but garbage in, garbage out. So we need to first do something before we integrate data from different sources. So the key technique here is getting data from the catalog, no matter which catalog. We want to first apply data imputation. We want to extract the structured data out of the unstructured titles, descriptions, bullets. And after that, we want to clean it up such that we can remove the noisy information and only keep the correct information. So in our team, we developed the system called AutoKnow. We increased the coverage of the structured data for products by 12 times at Amazon catalog, and also improved the accuracy by 8%. So the information is live on Alexa Shopping, Amazon Search, and the Amazon Detail page. In this talk, there are a lot of techniques we have developed, but we will focus on the web extraction part. And as I said, this is the sexy part and also one of the most challenging part. So for our web extraction, we focus on one particular type of websites. We call it semi-structured websites. Let me first show you several examples. And here is IMDb. I guess a lot of you are familiar with it. You can see for a movie, you can see the movie length, the genre, the release date, release country. Also, you can see some brief description, the director, writer, stars. It's not a big chunk of text or article, but much more of just basic facts about the movie and put into particular formats. Here is another example, and this is about a famous Indian movie. And here is another example about a famous Chinese movie. And they all share the similarity, not that much of text, but a lot of factual information about the movies. So why do we consider semi-structured websites? And this is because according to some previous projects, we can see big promise out of it. And that is the project Knowledge Vault that I was involved in when I worked for Google, where our goal is to extract knowledge from the web. And we consider 4 types of web content. The one is text, and these are the articles, news that we are all familiar with. The second one, we call it DOM trees, and this is the semi-structured data we have just seen. The third one is web tables. These are the tabular information on the web pages. And the last one is web annotations, which is the annotations on the HTML code according to some particular ontologies such as schema.org. So here for each type, we can see the numbers in the parentheses. That's the number of knowledge facts or knowledge triples extracted from each type of web contents. And we can see that from the semi-structured websites, we extracted 80% of all of the knowledge that we extracted. In addition, we also see the overlapping triples between different types of contents. And again, with this like a huge chunk of triples, the overlap is actually not that high with other type of web contents. And we see this much of extractions from semi-structured data. This is not surprising because oftentimes those websites have huge databases underlying it. And then it uses some particular template to populate each web page, and the data are from the database. So that's where we can find a lot of factual knowledge about real world. And another thing is Knowledge Vault has shown the accuracy of extraction from each type of web content. For texts, the accuracy is about 50%. This is 6 years ago. It is not high. And for semi-structured websites, it's still not high, 60%, but it is higher than web texts. That also shows some of the hope. Okay, so let's see what are the opportunities from the semi-structured data. And here I want to use the largest iceberg in the world as a metaphor. So if we look at a web page about this movie, When Harry Met Sally from Rotten Tomato, we can see a lot of information for those attributes that we are familiar with, such as genre, directed by, written by, and these are the attributes already modeled in the Freebase ontology. So Freebase is one of the largest free knowledge graph. And this is corresponding to the part of the iceberg that is above the water. So we know those relationships. In addition, we have attributes that existing ontology may not capture, such as in theaters, on disk, streamlining, and so on. And we did some analysis. We looked at 10 semi-structured movie websites, and we found the IMDb ontology, which is actually a very comprehensive ontology. It covers only 7% of the relations. And that could be considered as the part of the iceberg that is below the water. In addition, we also have a lot of domains that we are not familiar with. We know movies, but we may not know that much about Broadway shows. We may not know that much about video games. And we can consider that part as the part of the iceberg that is deep in the water. So we can see that semi-structured data can give us information about the known relations, the unknown relations, and also the unknown domains. That's why we are saying it is really, really a huge source of information and very promising. Okay, so where are we in terms of extracting knowledge from semi-structured websites? Well, we are at the tip. So our current technologies still heavily rely on manual annotations. And with the manual annotations, we are able to achieve a precision over 95%, very good. However, these are oftentimes about existing schemas from existing domains. And we see high quality oftentimes only on those easy attributes where there is a single value, such as date of birth. When there are multiple values, such as multiple actors of a movie, we don't see this very high quality anymore. And if we want to do automatic extraction, again, according to Knowledge Vault, the precision is still quite low, 63%. That's far away from being able to get into production in industry. So why is it so hard? Let's see what are the main challenges for extracting knowledge from semi-structured web. The first one is, even though we see a lot of similarity of the web pages from the same website, the format can actually vary slightly on different web pages. So here are two IMDb web pages, and we see that even though it looks very similar, but on the left page, we have director, writer, and the stars, and on the right one, we have only director and the stars. And we do not have writer information, possibly because we don't have that information in the database, in the underlying database. And then the next challenge, which is a much bigger challenge, is that different websites, the data are formatted totally differently. And here are the three examples we saw, and they look so different. It's very hard to imagine we can train one model to collect the information from all of these sources. So a natural thought when you see this is that, okay, let me train one model per website. But the next question is, to do such training, how can we collect the training data? It's almost impossible to manually collect training data for each predicate on each website, just because there are so many. Okay, so can we get the whole iceberg? To answer this question, let's first see, with all of the challenges, what are the opportunities? What are the kind of clues that we could leverage to extract knowledge from semi-structured websites? So I would say the first clue is the site-wide commonality. And if we look at these two pages from IMDb and also the previous examples as well, we can see there are a lot of commonalities. And in fact, if we look at the HTML code behind it, they are populated using the same template. And by the way, for the HTML code, it is structured in some DOM trees. We will refer to this concept. So it has a whole bunch of nodes nested within each other, and so give the structure of this DOM tree. So previous work have leveraged this commonality between the web pages within the same website. There are two major streams of work. One is wrapper induction, and here the idea is that since those HTML files are so similar, let's get manual annotation for a few pages, maybe 5 pages, maybe 10 pages, and then we could reverse engineer what are the DOM paths to generate particular predicate information, such as the born date. And with such manual annotation, we are able to achieve precision above 95%. And but again, as I said before, it is typically on easy attributes with single value. Another threat is relation extraction. So the idea there is, when I look at the HTML code, let me just treat it as normal text. And then I could apply the same techniques for relation extraction on normal text. So we will apply distance supervision to generate the training data. And when we found two entities somewhere on the page, we will look it up on the website, on the knowledge graph, and then decide what is the relationship in the knowledge graph, and accordingly guess the relationship on this website. In this way, we can generate a whole bunch of training data and use it to train a model per website. So the quality for that training data is actually very low because there are a lot of entities on each page, and so a lot of noises, a lot of wrong guess. As a result, the extraction precision is still low, only 60%. So we built this system called Ceres, which is also doing automatic extraction. It is different from the previous technique in two parts. The first one is we do two-stage extraction. Instead of looking at every pair of entities on a page, we will first find out what is the topic of each page. For example, on this web page, it is Alfred, and on this web page, it is Viola. And after we decide the topic, in other words, that will be the subject of all of the extracted triples from this page. We then find the attribute value pairs for this subject. So the second difference is that we are leveraging the site-wide global information when we generate the training data. Even in distance supervision in training data generation, we already explore the similarity across the different web pages. So for example, here we have born, we have died. It may not be easy to distinguish them, but we know born should have similar template, similar paths on each page. And that's where we will guess, hey, this is the born relationship together with all of the information from the knowledge graph. So that will help us to generate higher quality training data. With that, we are able to improve the precision from 63% to over 90%. To give you more details, so we applied this method on the SWDE benchmark data. The benchmark contains 4 different domains, and for each domain, it has 10 websites. And we applied our method on these 40 websites, comparing it with the previous wrapper induction work. So we can see that we get very high precision. And in addition, if we compare the F measure we get for our method and the F measure from rapid induction based on annotations, we get quite comparable F measure, except on books, because on books we have very, very little seed data in our knowledge graph. So we are not able to generate too many training labels. We applied the same techniques on 33 websites. Those are long tail movie websites, and it contains English and 6 other languages. It also contains a lot of long tail movies, such as animated films, documentary films. And in total, we have 400,000 web pages crawled by Common Crawl. So we are able to automatically annotate 16% of the pages. For each page we annotate, we are able to extract from 2.6 pages. In other words, we add 1.6 entities. And for each triple we annotate, we are able to extract 3 triples, or in other words, we add 2 more triples. And in total, we get 1.25 millions of extractions with precision 90%. So this figure shows the precision and the yield curve. As we change the confidence threshold, we see the precision will go up, and certainly the yield will go down. And at this point, annotated by this vertical yellow line, our precision is 90%, and we get about 1.25 millions of triples. So far, we are able to take care of the part of the iceberg above the water. So we are able to extract on those attributes that we already modeled in our ontology. Okay, so that's the first clue. The next clue is the layout on the page. So here is a page for this movie, and we know, let's say, the information about the genre, directed by, written by, according to our current knowledge graph. And then just by looking at the vertical and horizontal alignment, we are able to guess something else. First, because in theaters, is vertically aligned with these 3 attributes. So this is likely to be another attribute. And the second, because this July 12th is horizontally aligned with in theaters, and so this is likely to be the value for it. So by exploring this intuition, we developed open Ceres, which allows us to apply open information extraction such that we extract those attribute words as the attribute, and so we can extract knowledge for those new attributes. So we applied weak learning. We generate training data for existing attributes as what we did before, and then we look at the page layout and identify potential new attributes. And we do this through graph propagation, and this gives us an extraction of with precision 65%. To give you the details, again, this is on the SWDE benchmark, and we can see that the precision is lower, but we get a lot more new attributes. It used to be only 4 or 5 attributes, and then now it is 10x. And to show you some examples, for NBA player, our seed predicate is height, weight, and a team. That's what we have in the seed knowledge graph. And we are able to identify new attributes from the 10 NBA player websites about birth date, birthplace, salary, age, experience, position, college, year drafted, so on and so forth. We applied the same techniques on the 33 long-tail movie websites. And recall that this purple line is our Ceres curve for precision and yield. And now we have this green line for this open IE. So comparing with closed information extraction, now we added significant amount of knowledge for new predicates. But on the other hand, the quality is lower. And especially if we look at this line, these are the extraction for the new attributes. We see that the curve is still not in the best shape, and we still need to improve the precision. So this technique now allows us to extract unknown unknowns. In other words, we do not know those attributes before, but we are able to extract it. So that is part of the iceberg below the water. So the next clue is the visual patterns on the web page. So what do I mean? Here, I want to give you a quiz. I don't know how many people in the audience understand Korean. And so this is a web page in Korean. I guess most of you haven't seen it before. And for me, I don't understand those characters, and I don't understand what this web page is about. However, let me ask you, with this page, what part of the page represent the topic of this web page? So I guess it is this. This must be the topic for this page. That's also can be considered as the name of the main entity for this page. So what is a predicate for this entity? So there are quite a few, and this is one example. And what are the values for this predicate? So this is one value, another value. These are all values for this attribute. Is there any other value? Okay, so this 1961 is likely to be another value, even though we may not know what part is the attribute name. So for this totally new page for you, without understanding the domain, without understanding the language, without understanding any single token, you will be able to extract some knowledge triples like this, representing this part, and also some knowledge triples like this, even though you do not know exactly what is the predicate. So this is what human beings are able to do. And how can we teach computers to do the same thing? And here, the clues are the visual patterns. We do not know exactly how we get this, this decision regarding the extraction, but that might come from the font, color, and the size of those texts, and also the location and the alignment. So based on this, we developed zero-shot Ceres. And the goal is to enable ourselves to extract knowledge from totally new domains. And the key technique is to use graph neural network to learn the representation for each text field. And then we can decide the relationships between the text field according to the representations. So we achieved precision recall of 45% on totally new domains. And this is not high, much lower than closed IE or open IE. However, if we just compare with the baselines where we identify particular patterns, we have similar precision and our recall improved a lot. So here are the PR curve for the SWDE benchmark. And recall that we have 4 domains. If we train the model on one domain and look at the extraction from all of the 4 domains, that is this blue line. And if we train the model on one domain and extract knowledge from the other 3 domains, that gives us the PR curve as this orange line. So it is slightly lower, but on the other hand, not much lower. And that gives us the whole iceberg. So we are able to extract knowledge for domains that we have zero understanding before, or from a page where we do not necessarily know all of the text, all of the languages. Okay, so far I have been showing you the results, and you might be thinking, yeah, with these clues, if we can do that, this is cool. But what exactly is the secret sauce, and what exactly is the technique? So here I want to just highlight our technique for this zero-shot extraction. I want to call out my co-authors, so Colin and Prashant from Amazon and Hannah from UW. So the idea is this. So as I said, we will apply GN. And so this is graph neural net, and so we need a graph. And the graph is generated according to the page layout. Each node is a text field, such as Ethan Hawke's, and each edge represents the relationships. It could be horizontal edges, representing the left and the right relationship. It could be vertical edges representing the up and down relationship. It could also about the DOM edges representing the DOM siblings or DOM cousins in the DOM tree. So with this, we are able to build the graph, and the idea is whatever we learned about this text field can be propagated into its horizontal neighbor, into its vertical neighbor, and also to its DOM neighbor. So for each text field, we look at two different kinds of features. The first one is textual features. This is BERT embedding of the text there. This is also the IDF score, because normally the attribute names appear much more frequently on the website comparing with the attribute values. And also the text length. Normally, if it is very long string, it is less likely to be the attribute name. We also look at the visual features, such as the font size, color, the text field dimensions, whether this is bold, underlined, in italic, so on and so forth. So let me use this example to tell you the learning process. So this is a small area on the webpage about Smith College. We see the acceptance rate as well as the tuition. So for each text field, we capture the visual features and textual features and generate representations for them. Meanwhile, we generate the page layout graph, and we feed the tool into a graph attention network. This allows us to propagate the information among the neighboring text fields. And that generates the contextual feature for each text field. So the context feature will contain the features of the node itself as well as the neighbors. So now to train the extraction model for closed IE, our goal is to decide for each text field which relation it is corresponding to. So for example, for this $53,000, we take all of the visual, textual, and contextual features and feed it into a multi-class classifier. And then we decide, okay, this is a value of the relation tuition. And then for OpenIE, the idea is that we take two text fields. for example, tuition and 53,000. And for each text field, again, we will take the 3 representations. In addition, we will compare them pairwise and generate some pairwise features, such as the alignment features. And we feed all of this into a binary classifier to decide whether or not this is predicate value or attribute value pairs. So this is yes/no decision, binary decision. We do pre-training on some simplified IE tasks. For each text field, we do 3-way classification to decide if that is a relation string or an object string or some other strings. It could be totally irrelevant to any knowledge triples. And then we freeze the weights of the graph neural net and then train the extraction layer on top of it. So that gives us the model and the results we have just seen. Okay, are we there yet? So we have seen all of the different models for information extraction. And we see that unfortunately, the extraction quality drops from 90% to 60% to 40%. And when we want to launch something in industry, it has to be at least a 90% precision. So how can we improve the extraction precision to above 90%? And here, one idea is to combine zero-shot learning with distance supervision. Also, inspired by BERT embedding, we wonder if we could learn the representations for semi-structured data, such that we can use the representations to support different applications, not only the extraction application, but also question answering, search, or fact validation. So far, this is about extraction. So some of you might have been already thinking, if I get open IE extraction from this about a movie director and from this about movie directed by, how can I put all of them together? How can I decide if director and directed by are representing the same relationship? So this is very important for OpenIE. Given the time, I don't want to talk too much about it, and you are welcome to read our papers OpenKI to solve this problem, but the problem is not fully solved, and as you can see, the mean average precision is still quite low, so there is still room to improve to get good results. And here, just for some entertainment for this long talk, I would like to show you this cool animation where for every predicate extracted from each source, we generate the representation of the predicate. And then we can use the representation to decide whether they are the same predicate. We see some kind of clusters, but on the other hand, we see that film director, film writer, even film actor, there are a lot of overlaps because oftentimes one person is both director and writer of a movie. So the next thing is, we talked about linking the relations. The next thing naturally is how to link the entities. How can we decide if these two are the same person? And this is entity linkage, the first technique I mentioned at the beginning of the talk. And as I said, we are able to solve this problem with very high precision and recall for two sources. But when we come to web extraction, we have two challenges. The first challenge is we could have thousands of different types. And how can we train models for different types of entities, movies, songs, and TV shows, and Broadway shows, etc.? How can we link them? And the second challenge is we could have millions of sources. And I want to spend a little bit of time to tell you why this is hard, why we can train the model for 2 sources, but not for millions of sources. This is because the different sources have very different distributions. And we could train a model that does very well to connect music brains with another source, let's say Discogs, but when we apply the same model on last dot film, for whatever reason, if they miss the artist information, the model could perform very badly. And we did some initial study. We trained the model on 7 sources. And here we report the results on 4 of the sources. For track, artist, album, you can see the entity linkage, PRAUC, the area under the PR curve, is quite high, above 0.9. But on the other hand, if we train on 3 sources and apply the model on the rest of the 4 sources, you see this PRAUC dropped significantly. And so the question is, we won't be able to get the training data from so many different websites, and how can we train one model that applies everywhere? Okay, so several takeaways. We aim at harvesting knowledge from all semi-structured data on the web, and we aim at achieving both high accuracy, and also we are open, so we hopefully could extract unknown unknowns. And there are still a lot of research problems to solve to really get there. And I would like to advocate for 2 benchmark data sets. The first one is an extended SWDE benchmark. So SWDE is the benchmark I mentioned, and we significantly extended the benchmark with a lot of annotations on new attributes. And the second one is DI2KG, data integration to knowledge graph. This is a challenge benchmark, and it gives you data set not only to play with knowledge extraction, but also about knowledge alignment, knowledge integration. So with that, I'd like to thank you very much for listening, and I would love to answer questions.